I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on nuclear physics, nuclear fission, and nuclear fusion. In this video, we're going to be talking about nuclear physics, specifically nuclear fission and nuclear fusion. So let's start with nuclear fission. So this is a process in which a heavy nucleus splits into two smaller nuclei. During this process, the mass of the products is less than the original mass of the heavy nucleus. The process is triggered by a subatomic particle, usually a neutron, colliding with a heavy nucleus. So let's start by looking at a sample of uranium-235 and how that works. This is what was used in the Hiroshima bomb, as well as what's used in most nuclear power plants. So uranium-235 has a low energy neutron that collides with it. And what that does is it takes the uranium-235 and makes it U-236. Now, U-236 is very unstable and it starts spinning out of control. And when it spins out of control, what happens is it rips apart into two smaller nuclei. In some cases, it's barium-141 and krypton-92, and then also three neutrons that are also emitted during this process as well. So we take a look at our equation going from uranium-235 and a neutron to its products of three neutrons, krypton-92 and barium-141. You can see that the atomic number balances out, so that means that the charge is balanced out. And we can also see that the mass number adds up to 236 on both sides, where we've got 141, 92, and then three singular neutrons. Those add up to 236 as well. So if that's all conserved, where is this mass going that we lose from the products to the reactants? So if we look up on a table, we're going to have to go to a very large number of decimal places. A neutron has a unified atomic mass unit of this, and U-235 has a atomic mass unit of this. We add those together, and it gives us the 236.052,588 unified atomic mass units. Now, if we do the same thing for barium and for krypton, and we take a neutron and we multiply it by 3, and we add those values together, you can see that there's a small amount of mass that is not accounted for. Now, if we subtract these, the amount of mass that is not accounted for is about 0.186408 unified atomic mass units. Now, during this process, there's a lot of energy that is released during this nuclear fission process. Now, the amount of energy that is released during this process can be calculated using that mass that is unaccounted for. So the energy is going to equal m times c squared. Yes, Einstein's famous equation. Now, the famous equation is known as the energy mass equivalence. Now, to use the energy mass equivalent equation, what we're going to need to do is we're going to need to convert the unified atomic mass units either to kilograms and use 3 times 10 to the 8th meters per second, or we're going to have to convert it to mega electron volt per c squared. Now, in nuclear physics, it makes more sense to use mega electron volt per c squared, so that's what we're going to do. So the energy is going to equal the mass that is unaccounted for times 931 mega electron volt per c squared, and we multiply by the speed of light squared. Now we can see that we have speed of light squared twice, which is why it's easier to convert to mega electron volts. So we cancel out the c squareds and we multiply those together. And during one process, 173.545 mega electron volts of energy is released from that uranium-235. So if we look at what happens, U-235 is what's called a chain reaction nuclear fission because that neutron comes in, makes the U-236, and then splits into barium-141, krypton-92, and three neutrons. And now you can see those three neutrons are now going to move on and collide with three other U-235s. Now that's going to produce 9 more neutrons and so on and so forth. So that's why it's called a chain reaction. Now, barium and krypton are just two of the products that potentially could be produced in this nuclear fission process. There's other processes that can occur. So xenon and strontium could be a product, iodine and yttrium, antimony and niobium, to name several breakdowns of that nuclear fusion of U-235. But the key is that three neutrons are produced, which is what causes that chain reaction to cause the U-235 to continue to break down. Now we're going to talk about nuclear fusion. So it's when two light molecules collide and combine into a larger molecule. Their nuclei collide together. The decrease in mass of the combined nuclei produces a release of energy, much like in fission. Fusion also has a decrease in mass. Now, this can only occur at high temperatures. 10 to the 8th Kelvin, extremely high temperatures, are required to move the molecules fast enough to overcome the Coulomb force of repulsion. So the nuclei are both positive and they're going to repel each other. So the molecules have to be moving fast enough in order to collide and fuse together in order to form the larger molecule. Now, 90% of stars, including our sun, fuse hydrogen to produce helium and release energy in that process. So we're going to look at some particles that are used in fusion. So hydrogen is just one proton. That's what occurs mostly. In deuterium, which is also hydrogen, which has a neutron and a proton, this is the type of hydrogen that exists in water. So if we can use electrolysis to separate water, we can end up having deuterium as the hydrogen that is left over with the oxygen when we separate those two. Now, tritium is also hydrogen. It just has three nucleons, two neutrons, and one proton. And these are the three particles that mostly will be used in fusion to produce energy. And we're trying to do that using a fusion power plant, but that has not been created yet. We're still a long ways away from that. So we look at the process of nuclear fusion in our sun. So what happens is we have two helium nuclei and they are moving very rapidly and they collide and fuse together. And we will find the total mass of those hydrogen nuclei by adding the values together. Then what happens during the process of fusion is one of those protons changes to a neutron and releases a positron and a neutrino. So we end up with deuterium as a product of our first step in fusion. Now we can find the total mass of the deuterium and the positron and add those values together. And you can see the difference that we have is going to be 0.001. We multiply by 931, which is going to give us approximately 0.931 mega electron volts released in that process. Now, the second process is that hydrogen hits our deuterium and fuses together and makes a helium-3 and a gamma ray that are emitted. And during that process, we can see that there's a little bit of mass lost as well, and we can calculate the energy that is released during that process by using the equation E equals mc squared, and we end up with 5.491 mega electron volts, which is about 6 times more energy that is released from deuterium in hydrogen fusing than just two hydrogen. Now the process from here, a couple different things could happen. Is we have our helium-3 nucleus and another hydrogen could collide and fuse together with that. And then what happens during that process is one of those protons changes into a neutron, and the product is helium-4, a positron, and a neutrino. And you can see that there is mass that is lost during this process. So we convert that into the amount of energy, which the energy you can see is a much larger value when hydrogen and helium fuse together, 19.274 mega electron volts. So a lot of energy in the process of fusion. So if we look at the energy in our sun for the three different processes, we end up with a total energy of 25.969 mega electron volts. Now, one of the processes is the helium-3 colliding and fusing with hydrogen. Now, what could happen is that we have two helium-3s as a product. So this reaction would have to occur twice to have two helium-3s, and those collide and fuse together. And what those produce are now a helium-4 as well as two hydrogen atoms. So you end up with a product of two hydrogen atoms. Now this process releases 12.852 mega electron volts of energy if we went through the calculation. Now fusion power plants are ways off from producing energy for commercial use, a couple decades away. Now it has been done where we've had a fusion reaction that has been done in a small sample, but nothing to scale where it's enough to start producing energy for commercial use. Now, here are some of the processes that are being used in early development of fusion reactors, and we'll talk about why those are important. So, colliding two deuteriums, remember that is the hydrogen that is in water is deuterium. So, if we separated water by using electrolysis, we'd end up with deuterium as well as oxygen. We could collide the deuteriums to produce a helium-3 and a neutron, and that emits 3.27 mega electron volts when we went through the calculations. Now, two deuterium can also collide and produce a tritium and a hydrogen atom, which releases 4.03 mega electron volts. Now, tritium is radioactive, and having radioactive product is important because that's what we're trying to get away from. But tritium can be used in a reaction with deuterium to produce helium-4 and a neutron, which is 17.59 mega electron volts. So a large amount of energy is released with the tritium and deuterium. Now, tritium being a radioactive substance means that if we can use it, we don't have to have any waste because you can see the products of two deuterium is helium or hydrogen and a neutron. The neutron has a half-life of about 10 minutes before it ends up becoming part of another nucleus. And helium is just going to float around in the atmosphere. Tritium is the only one that is going to have radioactive properties, but we can use the tritium as another way to release a massive amount of energy by fusing it with deuterium. So this is an introduction to nuclear physics. This is fission and fusion. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below and subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.